Alright, here we go. This is 2017 number 1. I wrote down the points here. It was a 5.5 out of 10 was the national average on this problem. Number 4 we did just yesterday, and number 4 the national average was 1. Shoot, I should have had it handy. 1.8 out of 4. So here we go, just so you can kind of look as we go. Carbon tetrachloride, synthesized according to the equation above. Wonderful. Chemist runs a reaction. 120 Celsius, 25 liters. We got a temperature and a volume. It says here's a pressure of chlorine. How many moles of chlorine are in the container? At this point in our lives, we see temperature and pressure and volumes. We should be looking for PV equals nRT. And that is what we are doing here. So how many moles of chlorine? We're after moles of chlorine here for our N. So pressure of chlorine, 0.4 atmospheres. They gave us a volume of this thing, 25.0 liters. The number of moles is what we're after. It's moles of chlorine times atmospheres is 0.0821. Liters, atmospheres, moles, Kelvin is the unit on that thing. And then the temperature, 120 Celsius, is 393 Kelvin. Add the 273 to it. Make sure you're multiplying the right way on this. Multiply this side, divide by the other. In moles of chlorine, we end up getting 0.310 moles of chlorine. When in doubt, 3 sig figs. That's what I got for part A, number 1. Part A, number 2. Says how many grams of carbon disulfide are needed to react completely with the chlorine. So we take our moles of chlorine. This is a simple little stoich problem. We take our 0.310 moles of chlorine, and we are working towards what we want, grams of carbon disulfide. So moles of Cl2 come down. Moles of CS2 on top. There's our balance equation hidden up there. Moles to moles, 1 mole CS2, 3 moles of chlorine. And then we are moles to grams of CS2, 1 mole carbon plus 2 sulfur. Sulfur is about 32 apiece. Give us about 74 grams. Oop, I lied. About 76 grams. And that gives us 7.85 grams of carbon disulfide. There's part A. Pretty painless in part A. You get a point for PV equals nRT. You get 2 points for this. You get a point for using the correct mole ratio, so the 3-to-1 ratio, and then you get a point for the mass of carbon disulfide. And we're on to point B. Point B, at 30 degrees Celsius, the reaction is thermodynamically favorable, but no reaction is observed to occur. However, at 120, the reaction occurs at an observable rate. If you're at a temperature and it's thermodynamically favorable, but you don't see a reaction, the reason is because the activation energy is so high that that temperature doesn't give us enough kinetic energy to get very many particles to that activated complex. So at 120, then all of a sudden the reaction starts to take place. This is a collision theory question. So in B1, it says, explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120. So this is it. Increase in temperature causes collisions with more energy more frequently so more collisions reach the activated complex. You want to talk about orientation in there, more collisions, more correct collisions, or more collisions with correct orientation. But really this temperature is about colliding with more energy more frequently, and we reach that activated complex more often. Then part 2 here on B says the graph below gives us a distribution for the collision energies of the reactant molecules at 120. Draw a second curve on the graph that would show what's the distribution look like for collisions at 30 degrees Celsius. So right now we have all these collisions that are effective collisions. They reach the activated complex. So we need to show same number of particles, except they are less of them reaching the activated complex. And so this curve should be higher initially, like this, where more of the particles have less energy, and then that line should finish lower than the original, or the 120 degree number of particles. So there's less particles over here that have the required activation energy. You get 2 points there, a point earned for the curve that has a peak above and to the left of the given curve. So this is above and to the left, you get a point, and then you get a point for having less area under the curve after the activation energy in part 2 of B. Then we're to part C. Part C says sulfur with a chlorine here, some kind of compound or molecule, some kind of molecule here. It says in the box below, complete the Lewis electron dot diagram for S2Cl2 by drawing in all the electron pairs. And so I count them up. There's 7 there, 7 more there, that's 14, plus the 12 from the 2 sulfurs gives me 26 or 13 pairs. It is worth your time to add those up. Make sure you got those taken care of. You know there's at least one between each of the elements. There's 3 of our pairs. We got 10 pairs left. Take care of the outside ones first. 1, 2, 3, 4, 5, 6. And so we have 4 pairs left, and each of those sulfurs is going to get a couple pairs of electrons. And then go back and add them up. We got 3, 4, 5, 6, 7, 8, 9, 10 lone pairs, and then 3 bonded pairs. That should be our structure there. I encourage you, if you have time, to draw the dots on those things and not put them as bars. But bars for the bonded ones, I think, are healthy. Then it says, number 2, what is the approximate value of the chlorine to sulfur bond angle? What's the bond angle here for those 3 elements? And so we look at the central element, the sulfur. It has 4 domains, 2 bonded domains, and 2 lone pairs of electrons. And so if you have 2 bonded things and 2 lone pairs of electrons, it's approximately 104.5 degrees. It's not exactly that, but it's approximately that. They gave you credit for anything between 104 and 110 degrees there. That's part C. Point for the structure being right, point for the bond angle being right. They want to make sure you don't put 180 there. Good. You guys should be comfortable with water, right? Oxygen with 2 hydrogens and 2 lone pairs is 104.5. That's about what that should be. And then we're to part D. Part D says CCl4 can also be produced by reacting this guy with chlorine, and it gives us an equation. It says at the completion of the reaction, the chemist successfully separates the CCl4 from the hydrochloric acid by cooling the mixture to 70 degrees, at which temperature the CCl4 condenses and the HCl remains as a gas. D1 says identify all types of intermolecular forces in HCl. So hydrochloric acid there, everything has London dispersion forces, so it has London dispersion forces. And you don't have to draw anything, but you've got to recognize that that chlorine wants the electrons, has a greater electronegativity than hydrogen. And so the electrons are spending more of their time on chloride side, which means that molecule is going to have a negative and positive side on it. And so it also has dipole forces because it's a polar molecule. So London dispersion forces and dipole forces. And that one you get a point for having both of those types. If you only put one of those types, you don't get any point. And then one of my least favorite questions ever asked on the AP exam. This one hurts my feelings. It says, what can be inferred about the relative strengths of intermolecular forces of CCl4 and HCl? Justify your answer in terms of the information above. They told us that CCl4 condenses before HCl. CCl4 is nonpolar. It just has dispersion forces. HCl is polar with those dipole forces, but the intermolecular forces here are stronger than the intermolecular forces here. So you have to somehow, and it pains me because if something's polar, the tendency is polar things tend to be more attractive to each other than non-polar things, except this guy has so many electrons that all those electrons create dispersion forces that are greater than the dipole forces here. So what can be inferred about strengths? CCl4, trust the data, right? They're not making up data. I had kids come back in the test and go, I put that their data was wrong because HCl is a polar molecule and CCl4 is nonpolar. No. It tells you what happens, right? They're not making up the data here. And so CCl4 has stronger IMFs, stronger intermolecular forces. That's an appropriate abbreviation, by the way. Because it condenses at a higher temperature than HCl. And that's it. When the temperature's warmer, this guy condenses. He actually has bigger attractions, so he combines quicker than the HCl does, despite the fact that HCl is polar. That's it. That's number 1 on 2017. That's a really fair problem. And so hopefully you can find a bunch of those points. Look, if that last one freaks you out, we'll take 9s out of 10 all day. So you should be able to get the rest of that pretty comfortably. And then recognize what's happening there in that last part. See you soon.